Energy is never truly empty. Even in the deepest vacuum of space, far from stars and atoms, the universe still hums with quiet tension, with invisible fields holding more power than anything we can touch. Physics tells us that energy is not just something that moves through space, but something that can shape space itself. And under the right conditions, that shaping can become so intense that space bends, tears, or collapses into something entirely new. If this quiet journey brings you even a moment of peace or wonder, I'm deeply grateful you're here. A gentle like or a soft tap on subscribe helps keep these calm explorations alive, and I hold that support with sincere thanks. Now, let's begin with the first truth. A slow step inward toward the energy that could one day unmake space itself. Part 1. What does it mean for space to break? Space feels solid in its own way, steady and unchanging, a silent stage where the universe unfolds. Yet, physics tells us that space is not a rigid backdrop, but a flexible fabric capable of stretching, curving, and responding to energy. When scientists speak of space breaking, they don't mean shattering like glass, but reaching a limit where the familiar rules of distance and direction no longer apply. This is where energy stops being a passenger in space and becomes its sculptor, quietly testing how much the universe can hold. If you pause for a moment and consider where you are right now, it feels as though space around you is calm and dependable. The room does not bend. The distance between objects remains constant. Light travels in straight lines. These everyday experiences create the comforting illusion that space is fixed and absolute. For most of human history, this assumption felt not only reasonable, but necessary. Space was thought of as an empty container, a passive arena where matter moved but never altered the stage itself. That picture began to soften in the early 20th century. Albert Einstein showed that space and time are woven together into a single structure called spacetime, and that this structure responds to mass and energy. Gravity, in this view, is not a force pulling objects through space, but a gentle curvature of spacetime guiding their paths. Planets orbit not because they are tugged by invisible strings, but because space itself is curved around stars. This means that space is not merely something things exist within, it is something that can be shaped. A massive object like Earth slightly bends spacetime beneath your feet, though the effect is far too small to notice. A star bends it more. A black hole bends it so severely that paths through space begin to close in on themselves. And as the curvature increases, the familiar geometry you rely on quietly begins to fail. When physicists talk about space breaking, they are describing a point where this curvature becomes extreme enough that our equations stop giving reliable answers. Distances may shrink towards zero. Directions lose meaning. Time itself may slow, stretch, or fragment. This is not destruction in a dramatic sense, but a breakdown of description, where the language of physics no longer maps cleanly onto reality. To understand this, it helps to imagine space not as emptiness, but as something closer to a fabric. When nothing rests upon it, the fabric lies smooth and flat. Place a weight on it, and it curves. Add more weight, and the curvature deepens. But if you concentrate too much weight into too small an area, the fabric pinches, folds, or tears. In physics, energy plays the role of that weight, and space responds whether the energy comes from mass, motion, radiation, or pressure. Energy is subtle in this way. A beam of light carries energy. Heat carries energy. Even empty space carries a quiet background energy of its own. Under ordinary conditions, this energy is spread thinly enough that space remains stable. But when energy is compressed into an extremely small region, its gravitational influence grows intense. Spacetime curves more sharply, and the geometry we take for granted begins to strain. Black holes offer the clearest example. When a massive star exhausts its fuel and collapses, its core can compress so much mass energy into such a small volume that spacetime folds inward completely. Beyond a certain boundary, called the event horizon, all paths through space lead inward, not because something pulls harder, but because space itself no longer allows an outward direction. In this sense, space has already broken inside a black hole. The rules still exist, but they are no longer the ones you experience. At the very center of a black hole lies what physicists call a singularity, a point where density becomes infinite and curvature becomes undefined. This is not a place we can truly describe. It marks a limit where general relativity, our best theory of gravity, stops working. The equations predict infinities, which in physics is often a sign that the theory has reached the edge of its validity. Space has not just bent here, it has reached a conceptual breaking point. But black holes are not the only place where this idea arises. If you continue to zoom inward, beyond atoms and particles, you eventually approach the Planck scale. This is the smallest meaningful length known in physics, around 1/10 billion trillion trillionth of a meter. At this scale, quantum effects become so strong that space-time itself is thought to fluctuate. Smooth geometry dissolves into something more restless and grain-like. Here, space does not behave as a continuous fabric at all. It flickers, it jitters. Distances lose their stability. Time may no longer flow smoothly from one moment to the next. This is another sense in which space can be said to break, not through collapse, but through uncertainty. Our familiar picture of reality fades into probabilities and quantum foam. What makes this idea unsettling is that it suggests space has limits, just as matter does. There is a smallest distance that can be meaningfully defined, a maximum curvature that can be described, a point beyond which measurement itself becomes impossible. These are not limits imposed by technology, but by nature itself. The universe appears to protect its deepest structure behind boundaries we cannot cross. And yet, this breaking is not chaotic or violent in the way we often imagine destruction. There is no explosion when space-time reaches its limits. There is only silence and mathematical uncertainty. The universe does not tear itself apart loudly. It simply stops answering our questions in the language we know. This realization changes how scientists think about reality. It suggests that space is not fundamental, but emergent, arising from deeper principles that reveal themselves only at extreme energies. Just as temperature emerges from the motion of particles, space-time itself may emerge from something more basic. When those underlying structures are pushed too far, the illusion of smooth space dissolves. From your perspective, resting here and listening, this might all feel distant and abstract. But there is something quietly comforting in it. The same laws that allow space to bend and break also allow it to remain stable for billions of years. The universe naturally avoids extremes. Energy spreads out, curvature relaxes, space heals itself by expanding and cooling. You live in a region where space-time is calm enough to hold galaxies, stars, planets, and life. The breaking points exist, but they are tucked far away, behind horizons and scales we rarely encounter. They remind us not of fragility, but of balance, of how much structure exists simply to allow things to be as they are. As you breathe gently now, space around you is doing its quiet work, holding form, maintaining distance, allowing light to travel and time to flow. It feels solid because, on human scales, it is. But beneath that calm lies a deeper truth. Space is active, responsive, and finite in its tolerance. And as we continue this quiet journey, one question naturally follows. If space can bend and even break under enough energy, how much energy would it take to push it that far? Part 2. The invisible fabric beneath everything. Long before galaxies or atoms existed, space itself came into being with structure woven into its depths. Einstein showed us that space and time are bound together, forming a single fabric called spacetime. This fabric is usually calm and smooth, but it is never truly empty. Even now, as you rest and listen, space-time beneath you is subtly curved by Earth's mass and by the energy flowing through the cosmos. Understanding this invisible structure is the first step toward understanding how it might one day be overwhelmed. To the human senses, space feels like nothing at all. You cannot touch it, hear it, or feel it pressing back against you. And yet, physics tells us that space is not absence. It has shape, it has geometry, it has rules. Every movement you make, every beam of light that reaches your eyes, every second that passes is guided by this unseen framework. Space is not a void waiting to be filled. It is the medium through which everything happens. Einstein's insight was to realize that time cannot be separated from space. Before his work, time was thought of as a universal clock, ticking the same way everywhere. Space was thought of as a fixed stage, but the universe did not agree. Experiments showed that clocks tick differently depending on motion and gravity, and that distances change depending on perspective. The only way to make sense of this was to unify space and time into a single entity, spacetime. In this picture, every event has a location not just in space but in time as well. And the geometry of spacetime determines how objects move. When spacetime is flat, motion follows straight paths. When spacetime curves, paths bend. This bending is what we experience as gravity. It is not a force pulling things inward, but the natural motion of objects following the shape of spacetime itself. You can imagine this fabric as endlessly extending, smooth and continuous. But even in its calmest state, it is not empty. Quantum physics tells us that space is filled with fields, fluctuating quietly even at absolute zero. Particles appear and vanish, energy rises and falls in tiny amounts. This restless background is known as the quantum vacuum, and it means that space is always active, even when nothing appears to be happening. These fluctuations are usually insignificant, averaging out over time. But they remind us that space is not inert, it is dynamic at the deepest level. The smoothness we experience is an approximation, a large-scale calm that emerges when countless tiny motions blend together. Much like the surface of a quiet lake hides the movement of individual water molecules beneath. Gravity adds another layer to this story. Any mass or energy placed into spacetime changes its shape. Earth curves spacetime enough to hold the moon in orbit. The sun curves it more strongly, guiding the motion of planets. Entire galaxies curve spacetime on enormous scales, influencing the paths of neighboring galaxies through invisible wells of gravity. And this curvature does not stop at the edge of matter. It extends outward indefinitely, fading slowly with distance. As you lie still, your body contributes to this geometry in an almost immeasurable way. Your mass slightly curves spacetime beneath you. The walls around you do the same. The planet beneath them curves it far more. All of these effects overlap, layering together into a complex, continuous structure that holds everything in quiet balance. What makes spacetime remarkable is how resilient it usually is. It can bend and stretch without tearing. It can ripple as gravitational waves passing through the universe gently compress and expand space itself. These waves, detected for the first time in 2015, were predicted a century earlier by Einstein's equations. They confirmed that spacetime is not just a mathematical idea, but something physical enough to vibrate. Yet resilience is not the same as invincibility. The equations of general relativity allow spacetime to curve more and more sharply as energy density increases. There is no built-in limit within the theory itself. Push enough energy into a small enough region, and the curvature grows without bound. This is where the idea of spacetime being overwhelmed begins to emerge. At moderate energies, spacetime responds smoothly. At extreme energies, the response becomes nonlinear and unpredictable. This is especially true when quantum effects are involved. General relativity describes spacetime on large scales, while quantum mechanics governs the smallest scales. Each works extraordinarily well in its own domain. But when both must apply at once, near singularities or the very beginning of the universe, the two frameworks clash. This clash suggests that spacetime itself may not be fundamental. It may be an emergent phenomenon, arising from something deeper. Just as temperature emerges from the motion of particles, spacetime may emerge from interactions at a more basic level. In such a view, the fabric can unravel not because it is damaged, but because the conditions that sustain it no longer apply. One place where this becomes evident is at the Planck scale. At distances this small, quantum fluctuations in energy are so intense that they significantly disturb spacetime geometry. Space may no longer be smooth. Time may no longer flow continuously. Instead, reality becomes granular, probabilistic, and unstable. The familiar fabric dissolves into something more abstract, where concepts like before and after, here and there, lose clarity. This does not mean the universe becomes chaotic. It means our descriptions fail. The rules that guide your daily experience simply do not apply at that level. Space-time has not exploded. It has slipped beyond the reach of our intuition. In the early universe, such conditions were common. Just after the Big Bang, the entire cosmos was compressed into a state of immense energy density. Space-time itself was intensely curved, dynamic, and rapidly changing. As the universe expanded and cooled, space-time relaxed, smoothing out into the calm structure we inhabit today. In a sense, the universe has already survived being overwhelmed once. This history is quietly written into the cosmic microwave background, the faint afterglow of the early universe. Tiny variations in this ancient light reflect minute fluctuations in space-time itself, frozen in place as the universe cooled. They are a reminder that space-time has a history, one shaped by energy, expansion, and change. What is striking is how stable things have become since then. For billions of years, space-time has maintained conditions gentle enough for stars to burn steadily, planets to form, and life to evolve. This stability is not guaranteed. It is the result of delicate balances between gravity, expansion, and energy distribution. When physicists consider how space-time might one day be overwhelmed again, they are not predicting disaster, but exploring boundaries. They are asking how much curvature space-time can sustain, how much energy it can absorb, and under what conditions the smooth fabric might give way to something new. For you, listening now, this invisible fabric continues its quiet work. It holds the planet together, it carries light from distant stars, it allows time to pass gently from one moment to the next. You are supported not by solid ground alone, but by the geometry of the universe itself. There is something deeply calming in that thought. The same structure that can bend and break at extremes is the one that cradles you in stillness now. Space-time does not strain under ordinary conditions. It rests, balanced and reliable, shaped by forces so ancient and consistent that they fade into the background of experience. And yet, beneath that calm, the deeper question remains, waiting patiently. If space-time is a fabric with limits, what kinds of energy are capable of pushing it beyond them? Part 3. How energy shapes reality. Energy is not just motion or heat or light. In modern physics, energy is a source of gravity, just as powerful as mass itself. According to general relativity, concentrating energy in one place tells space-time how to bend. The more energy you pack into a smaller region, the deeper the curve becomes. This quiet relationship between energy and geometry governs everything from planetary orbits to the slow drift of galaxies, and it sets the stage for far more extreme possibilities. When you think of gravity, it's natural to picture weight, solid objects, planets and stars pulling on one another through empty space. But gravity does not actually care whether something is solid or visible. It responds to energy in all its forms. A beam of light has gravity, heat has gravity, pressure has gravity. Even the restless energy of empty space contributes to the shape of the universe. This is one of the most subtle shifts Einstein introduced. In his equations, mass is only one expression of energy. The true source of gravity is something called the stress-energy tensor, a mathematical object that includes mass, motion, pressure, and energy flow. In other words, space-time listens not just to what exists, but to how intensely it exists. Under everyday conditions, this effect is gentle. The energy stored in sunlight warms your skin, but it does not noticeably curve space. The heat inside your body contributes to gravity, but the influence is unimaginably small. Space remains calm because energy is spread out, diluted across large volumes. Geometry responds quietly, almost imperceptibly. But as energy becomes concentrated, the response changes. When a star ignites nuclear fusion, enormous amounts of energy are released in its core. That energy contributes to the star's gravity just as much as the mass of the atoms themselves. The star balances on a delicate edge, outward pressure from fusion pushing against inward curvature of spacetime. This balance can last for billions of years, a long conversation between energy and geometry held in silence. On larger scales, the same principle governs galaxies. Entire swarms of stars orbit around invisible wells of curved spacetime, shaped not only by visible matter, but by vast amounts of unseen energy we call dark matter. Even though we cannot touch or see it directly, its gravitational influence tells us it is there, shaping reality by how it bends spacetime. Energy does not need to shine to matter, it only needs to exist. One of the most striking demonstrations of energy shaping reality comes from light itself. Photons have no rest mass, yet they follow curved paths when they pass near massive objects. This bending of light, called gravitational lensing, is not because gravity pulls on light as a force. It happens because spacetime itself is curved, and light simply follows the geometry laid out before it. When astronomers observe distant galaxies whose light has been stretched into arcs and rings by gravity, they are witnessing energy shaping the universe on the largest scales. The gravity doing the bending comes from energy distributed across entire clusters of galaxies, sculpting spacetime over millions of light years. As energy density increases further, the relationship becomes more dramatic. Near neutron stars, matter is crushed so tightly that atomic structure collapses. Energy density becomes extreme. Spacetime curves sharply, and time itself begins to slow. A clock placed near a neutron star would tick noticeably slower than one far away. Energy has reshaped not just space, but time. Black holes represent the most extreme outcome of this process. When energy is compressed beyond a certain threshold, spacetime no longer finds a stable configuration. Collapse becomes inevitable. The curvature deepens until a horizon forms, beyond which no information can escape. This is not destruction in the violent sense, but a reconfiguration so severe that outside observers lose access to what lies within. Inside a black hole, energy density continues to rise as collapse proceeds. According to our current theories, this leads to a singularity, a region where curvature becomes infinite. At this point, spacetime itself ceases to be well-defined. Energy has not just shaped reality, it has pushed it beyond the limits of description. Yet this shaping is not limited to dramatic cosmic objects. The early universe itself was shaped by energy in its purest form. Shortly after the Big Bang, the universe was filled with radiation and fields at unimaginable energy densities. Spacetime was intensely curved everywhere. There were no stars or atoms yet, only energy interacting with geometry in a rapidly expanding cosmos. As the universe cooled and expanded, energy spread out. Curvature softened, space flattened on large scales. This transition allowed structures to form gradually, guided by small differences in energy density. The galaxies you see today are the fossilized imprint of how energy once shaped spacetime when everything was closer together. Even now, energy continues to sculpt reality quietly. Dark energy, a uniform energy permeating space, drives the accelerated expansion of the universe. It does not clump like matter. Instead, it gently stretches spacetime itself, increasing the distance between galaxies over time. This stretching is subtle but relentless, changing the geometry of the universe on the largest possible scales. What makes energy so powerful is not just how much of it exists, but how it is arranged. Spread thinly, energy creates only mild curvature. Concentrated tightly, it can overwhelm spacetime entirely. This sensitivity is what gives rise to natural limits. There's a point beyond which geometry cannot respond smoothly. Instead of bending more, it changes character. At extremely small scales, quantum effects enter the picture. Energy fluctuations become unavoidable. Even in empty space, uncertainty ensures that energy briefly spikes and falls. Normally, these fluctuations average out. But near the Planck scale, they become large enough to significantly disturb spacetime geometry. Space itself may fluctuate, losing its smoothness. Here, the idea of energy shaping reality reaches its most abstract form. Reality itself becomes probabilistic. Geometry is no longer fixed. time may fragment. The notion of a continuous space-time fabric dissolves into something more restless and uncertain. Energy has not destroyed space, but revealed that space was never fundamental to begin with. For physicists, this realization is both unsettling and inspiring. It suggests that space-time emerges from deeper rules written in terms of energy and information rather than distance and duration. When energy reaches certain thresholds, those deeper rules take over and the familiar world fades. For you resting now, this story unfolds quietly beneath your awareness. The energy in your body, the warmth in the air, the light reaching your closed eyes, all contribute in their own small way to the geometry of space-time around you. It is a tiny influence, but it is real. You are not just in the universe, you are part of the equation that shapes it. There is something calming in knowing that reality is not rigid, but responsive. That space listens. That energy and geometry are in constant dialogue, adjusting and balancing across scales far beyond human perception. The same laws that allow space to curve under extreme energy also allow it to remain stable and gentle where you are now. As this section draws to a close, one truth stands quietly at its center. Energy is not merely something that happens within reality. It is one of the things that defines reality itself. And as we continue this calm exploration, one question lingers softly in the background. If energy can shape space-time so profoundly, what happens when that energy is no longer contained at all? Part 4. The calm power of the vacuum. Empty space is not truly empty. Quantum physics reveals that even the vacuum seethes with temporary fluctuations, particles appearing and vanishing in silent pairs. This background energy, called vacuum energy, fills all of space uniformly. It rarely makes itself known, yet its presence may shape the expansion of the universe itself. Here, destruction does not arrive as an explosion, but as a gentle, persistent pressure that never quite goes away. When you imagine a vacuum, you might picture perfect nothingness, a region scrubbed clean of matter, light, and motion. But nature does not allow such absolute emptiness. Even when every particle is removed, even when temperature is lowered as far as possible, space refuses to become still. Something remains. A quiet activity beneath the surface, a restless hum that cannot be turned off. This comes from one of the deepest principles in quantum physics: uncertainty. At the smallest scales, nature does not permit exact stillness. Energy and time are linked in such a way that energy can briefly appear, so long as it disappears quickly enough. These fleeting borrowings of energy manifest as virtual particles, pairs that form and vanish before they can be directly observed. They leave no tracks, they make no sound. Yet their effects are measurable. This constant flickering is what we call vacuum fluctuations, and taken together, across all of space, they give rise to vacuum energy. It is not concentrated in stars or galaxies. It does not clump or flow. It simply exists everywhere, evenly spread, woven into the fabric of space-time itself. Because it is so uniform, vacuum energy is easy to overlook. Gravity responds most strongly to differences, to concentrations and gradients. A perfectly even background produces no obvious pull in any direction. And so for a long time, vacuum energy was treated as a mathematical curiosity rather than a physical presence. But the universe does not ignore it. In Einstein's equations, even empty space can possess energy, and that energy influences the curvature of space-time. When this idea is applied on cosmic scales, something remarkable emerges. Instead of pulling space inward like matter does, vacuum energy appears to push space outward. It acts as a kind of pressure built into emptiness itself. This pressure is subtle. It does not shove galaxies apart suddenly. It does not tear stars from their orbits. Instead, it works slowly, persistently, adding up its influence over billions of years. And this slow influence may explain one of the most surprising discoveries in modern cosmology. In the late 20th century, astronomers expected the expansion of the universe to be slowing down. Gravity, after all, pulls matter together. An expanding universe filled with galaxy. Matter should gradually decelerate. But when scientists measured the distances to faraway supernovae, they found the opposite. The expansion of the universe is accelerating. Something is pushing space itself to stretch faster and faster. The simplest explanation is vacuum energy, often referred to as dark energy. Not dark because it is sinister, but because it does not emit light and does not interact in familiar ways. It reveals itself only through its effect on spacetime. A quiet pressure, uniform and constant, gently urging the universe to grow. What makes this power so unsettling is how calm it is. There is no violence in its action, no shockwave, no boundary. Every region of space feels it equally. Galaxies drift apart not because they are fleeing an explosion, but because the space between them is slowly swelling. From your perspective, this expansion is imperceptible. The atoms in your body are held together by forces far stronger than the stretching of space. Your planet remains intact. Your galaxy remains bound. The vacuum's influence only becomes dominant across vast intergalactic distances where gravity grows weak and distances grow immense. Yet over enough time, even this gentle pressure reshapes the universe. As space expands, galaxies move farther apart. Light traveling between them stretches, shifting toward longer wavelengths. Eventually, distant galaxies slip beyond the cosmic horizon, becoming unreachable, their light never able to arrive. The universe grows quieter, emptier, more isolated. This is not destruction in the traditional sense. Nothing is torn apart locally. No structures collapse. Instead, connection fades. The universe does not end with a bang, but with a thinning, a gradual quieting as space grows larger and colder. What makes vacuum energy even more intriguing is that its value appears finely tuned. Calculations from quantum physics predict a vacuum energy density far larger than what we observe, off by an almost unimaginable factor. And yet, the actual vacuum energy is small enough to allow galaxies, stars, and life to exist for billions of years. Why it has this value remains one of the deepest unanswered questions in physics. Some theories suggest that many possible vacuum states exist, each with different energies. Others propose that vacuum energy changes over time. Still others suggest that we observe this particular value simply because regions with much stronger vacuum energy would never form complex structures. Whatever the explanation, the vacuum is not passive. It is not a blank canvas. It is an active participant in the universe's evolution. At the smallest scales, vacuum fluctuations influence particle behavior. At the largest scales, vacuum energy governs the fate of the cosmos, and in between, it remains almost perfectly silent, doing its work without announcement. There is something profoundly calming about this. The most powerful force shaping the universe's future does not roar or blaze. It presses gently, constantly, patiently, like a tide so slow that no wave can be seen, yet so vast that continents eventually feel its pull. Even the idea of space being destroyed takes on a different meaning here. Vacuum energy does not rip space-time apart. It stretches it, it thins it. It may, over inconceivable timescales, dilute matter so completely that meaningful interactions become rare. Space survives but becomes empty of stories. And yet, this same vacuum energy once played a very different role. In the earliest moments after the Big Bang, a form of vacuum-like energy may have driven a brief period of rapid expansion known as cosmic inflation. During this time, space expanded exponentially fast, smoothing out irregularities and setting the stage for everything that followed. That ancient vacuum energy eventually faded, leaving behind a gentler version that now guides the universe's late-time expansion. In this sense, the vacuum has already reshaped reality once, dramatically and completely. And it did so without violence, without sound, without warning. Just expansion, unfolding faster than intuition can follow. As you lie still, the vacuum around you is unchanged. It presses equally in all directions. It does not disturb your rest. The calm you feel is not separate from it. It exists because of it. Because the universe has settled into a state where vacuum energy is mild enough to allow stability, yet strong enough to keep the cosmos evolving. This balance will not last forever, but it will last far longer than any human timescale. Long enough for stars to live and die. Long enough for galaxies to drift. Long enough for countless quiet moments like this one. The vacuum is a reminder that the most profound forces do not need to announce themselves. That emptiness can be full. That stillness can shape everything. And as this quiet chapter closes, another question begins to form, slowly and gently. If even empty space carries power, how much pressure can space-time endure before it finally gives way? Part 5. When density becomes dangerous. As energy density increases, strange things begin to happen. Space responds not linearly, but dramatically. A small increase in energy packed tightly enough can lead to enormous gravitational effects. At extreme densities, the equations of physics predict that space-time can fold inward, creating horizons beyond which nothing can return. This is not chaos, but an orderly consequence of natural laws reaching their limits. In everyday life, density feels intuitive. Pack more people into a room and movement becomes harder. Compress air and it pushes back. Increase pressure gradually and the response feels predictable. But the universe does not always behave this gently. When it comes to space-time, density is not merely a matter of crowding. It is a trigger that can fundamentally alter the structure of reality. Energy density refers to how much energy exists within a given volume of space. Spread thinly across vast distances, energy has little influence on geometry. But concentrate that same energy into a small enough region, and space-time reacts sharply. This is because gravity does not scale smoothly with density. It accelerates. The tighter energy is packed, the more intensely space-time curves, and the faster that curvature deepens. This nonlinear response is one of the universe's quietest dangers. There is no warning sign as density increases. No visible threshold you can point to and say, here is where things become unstable. Everything appears normal until, suddenly, it is not. Stars offer a calm example of this balance. Inside a star, energy from nuclear fusion creates outward pressure that resists gravitational collapse. Gravity presses inward. For millions or billions of years, these two influences hold one another in steady equilibrium. Density rises toward the core, but not enough to overwhelm spacetime's ability to respond smoothly. But when a massive star exhausts its nuclear fuel, that balance dissolves. Energy production drops. Gravity gains the upper hand. The star's core begins to collapse under its own weight, compressing mass and energy into an ever smaller volume. Density rises rapidly, and spacetime curves more steeply with every moment. For smaller stars, collapse halts when electrons or neutrons push back, creating white dwarfs or neutron stars. These objects are already extreme. A teaspoon of neutron star material would weigh billions of tons. Time slows near their surfaces, space bends sharply, and yet space-time still holds. For the most massive stars, even this resistance is not enough. Collapse continues. Density climbs past every known stabilizing force. And then something remarkable happens. A boundary forms in space-time itself. This boundary is the event horizon. The event horizon is not a physical surface. It is not a wall or a shell. It is a geometric threshold. Beyond it, space-time is curved so severely that all possible paths lead inward. Not because gravity pulls harder than light can escape, but because outward directions no longer exist. Space itself points inward. From the outside, this process appears almost gentle. The collapsing star fades from view. Its light dims. Time near the forming horizon slows to a crawl. There is no explosion at the boundary, no sudden flash. The universe remains quiet as space-time seals itself off. This is what it means for density to become dangerous, not destructive in a violent sense, but transformative. Density does not tear space-time apart. It reorganizes it so completely that familiar concepts cease to apply. Inside the horizon, density continues to rise. According to general relativity, collapse proceeds until energy is compressed into an infinitely dense point, a singularity. At that point, curvature becomes infinite and the equations lose meaning. Space and time no longer behave as dimensions we can define. The theory breaks down, not because reality explodes, but because our description fails. This breakdown is not unique to black holes. It appears wherever density reaches extremes. In the earliest moments of the universe, all energy was packed into a tiny volume. Space-time itself was dense, hot, and violently curved. The Big Bang was not an explosion in space, but an expansion of space from a state of extreme density. As the universe expanded, density dropped, space-time relaxed, geometry smoothed out. The danger passed, not because laws changed, but because energy spread out. Density fell below critical thresholds, allowing structure to form. This pattern reveals something profound. Space-time is not fragile, but it is conditional. It remains smooth and stable only when energy density stays within certain bounds. Push beyond them, and space-time responds decisively. What makes this especially intriguing is how sudden the transition can be. There is no gradual warning. As density increases, everything seems manageable until a critical point is crossed. Then, horizons form. Time stretches, paths close. The universe quietly redraws the map of what is possible. This is why physicists speak of thresholds rather than gradual failure. Density does not slowly degrade spacetime. It flips it into a different regime, one governed by different rules, where information cannot escape and geometry dominates everything else. Quantum physics complicates this picture further. At extremely high densities, quantum effects become unavoidable. Energy fluctuations grow large. Uncertainty prevents matter from being pinned down precisely. In these regimes, spacetime itself may fluctuate, making the notion of a single, smooth geometry meaningless. Some theories suggest that quantum effects might prevent true singularities from forming, replacing them with finite, though extreme, states. Others suggest that spacetime could transition into an entirely new phase. In either case, density is the catalyst. It is the quiet pressure that forces reality to reveal its deeper structure. From a human perspective, these ideas can feel unsettling, but there is also something reassuring in their consistency. Density becomes dangerous only under conditions far removed from everyday experience. Nature is remarkably good at avoiding extremes. Energy spreads, systems cool, stability is favored. The atoms in your body are nowhere near such densities. The earth beneath you is comfortably stable. Even the sun is far from collapse. Dangerous density exists only in rare cosmic events or in the distant past and future of the universe. And yet, understanding these limits matters. They tell us that reality is not infinitely flexible. There are boundaries built into the fabric of existence. Cross them, and the universe does not panic. It adapts. As you breathe slowly now, space around you remains calm because energy is diffuse, density is low, geometry is gentle. The same laws that allow black holes to form also ensure that your surroundings remain steady and predictable. There's a quiet elegance in this balance. The universe allows extraordinary extremes, but only under extraordinary conditions. Most of the time, it rests in a state of graceful moderation. Density, then, is not an enemy. It is a measure of intensity, a reminder that how much exists matters less than how tightly it is packed, and that at certain thresholds, reality chooses transformation over collapse. As we continue this calm exploration, another question begins to emerge just beyond the horizon of this chapter. If density alone can reshape spacetime so completely, what happens when it becomes impossible to increase it any further? Part 6. Black holes as a warning sign. Black holes are not cosmic accidents. They are the universe's response to energy and mass pushed too far. When a region of space contains more energy than spacetime can support, collapse becomes inevitable. The event horizon marks a boundary where space tilts so steeply that even light cannot escape. Black holes show us that space can be damaged, reshaped, and sealed off, all without violence or sound. When most people imagine black holes, they picture destruction, a cosmic monster tearing stars apart, swallowing everything nearby. But this image misses something essential. Black holes are not agents of chaos, they are symptoms. They are what space-time does when the balance between energy and geometry is pushed beyond its limits. In that sense, black holes are not exceptions to the laws of physics, they are confirmations of them. To understand why, it helps to remember that gravity is not a force in the usual sense. It is the shape of space-time itself. When mass and energy curve space gently, objects follow predictable paths. When that curvature deepens, paths bend more sharply, and when curvature becomes extreme, space-time closes in on itself. A black hole forms precisely at that point. The event horizon is often described as the point of no return, but this can be misleading. Nothing special happens at the horizon itself, at least not locally. There is no sudden wall, no flash of light. If you could cross it without being torn apart by tidal forces, you would not notice the moment you passed it. The danger is not at the boundary, but in what the boundary represents. Beyond the horizon, all possible future paths lead inward. This is not because gravity suddenly becomes stronger than light, but because the geometry of space and time has rearranged itself. Time itself tilts toward the center. Moving forward in time means moving deeper into the black hole. Escape is not forbidden by force, but by structure. This is why black holes are such powerful warning signs. They show us that space-time is not infinitely adaptable. There are configurations it cannot sustain. When energy density crosses a critical threshold, space-time does not stretch a little more, it changes phase. The formation of a black hole is surprisingly quiet. From far away, A8's collapsing star appears to slow and fade. Its light grows redder, dimmer. Time near its surface stretches. The universe does not announce the birth of a black hole with noise or fire. It simply rearranges itself. This silence is important. It tells us that space-time does not resist collapse in a dramatic way. There is no tearing, no rupture. The geometry flows smoothly into a new configuration. The horizon forms naturally as a consequence of the equations. Inside the horizon, our understanding becomes uncertain. According to general relativity, collapse continues until a singularity forms, a region where density becomes infinite and curvature diverges. But most physicists believe this signals the breakdown of the theory, not the presence of actual infinities in nature. In other words, black holes do not necessarily contain infinite density. They contain regions where our descriptions fail. This makes them invaluable. Black holes are not just exotic objects, they are laboratories where gravity, energy, and space-time reveal their limits. They show us what happens when known laws are stretched to the edge of their applicability. Consider how small black holes can be. A black hole with the mass of the Sun would have an event horizon only a few kilometers across. All that mass, all that energy, confined to a region smaller than a city. The density required to achieve this is staggering. And yet, once formed, the black hole is remarkably simple. From the outside, a black hole is defined by only a few properties: mass, charge, and spin. Everything else about the matter that formed it disappears behind the horizon. This simplicity is not an accident. It reflects the fact that space-time itself has taken over. The details of matter no longer matter. This is one of the deepest lessons black holes teach us. When space-time is pushed too far, information about the past is hidden. Not destroyed perhaps, but rendered inaccessible. The universe enforces limits on what can be known and shared. This idea has profound implications. It suggests that there are boundaries not just in space, but in knowledge itself. Regions beyond which information cannot reach us. Limits that are not technological, but fundamental. Black holes also show us that space can be sealed off. A black hole does not remove space from the universe. It creates a region that is causally disconnected. Events inside cannot influence the outside world. Space remains, but it becomes private, inaccessible, folded inward. In this way, black holes act like scars in space-time, permanent reminders that density once became too great in that region. They mark places where the universe reached a critical threshold and responded by isolating the damage. This isolation is not punitive. It is stabilizing. By sealing off extreme regions, space-time prevents their effects from spreading uncontrollably. Black holes allow the rest of the universe to remain calm, predictable, and habitable. They are containment mechanisms built into the laws of physics. Even on cosmic scales, black holes play this quiet role. Supermassive black holes sit at the centers of galaxies, millions or billions of times the mass of the Sun. They do not consume their galaxies. Instead, they influence them gently, regulating star formation through feedback processes that unfold over millions of years. Once again, violence is not the defining feature. Balance is. Black holes also offer hints about what lies beyond our current understanding. When physicists try to combine quantum mechanics with general relativity, black holes become focal points. Questions about information, entropy, and the nature of space-time itself all converge here. One of the most famous puzzles is the information paradox. If information falls into a black hole and cannot escape, what happens to it when the black hole evaporates through a process known as Hawking radiation? Does information disappear forever, violating fundamental principles, or is it somehow preserved in subtle correlations? These questions arise because black holes sit at the boundary between what space-time can handle and what it cannot. They are warning signs that our current frameworks are incomplete, yet even here, the universe remains restrained. Hawking radiation is incredibly weak. A stellar mass black hole would take far longer than the current age of the universe to evaporate. Nothing sudden occurs. The process is slow, patient, almost gentle. As you rest now, it may be comforting to know that black holes are not threats to your existence. They are rare, distant, governed by rules that favor stability over chaos. The nearest known black hole is thousands of light years away, quietly orbiting the galaxy without disturbance. Their importance lies not in fear, but in insight. Black holes show us that space-time can be reshaped beyond recognition without breaking apart violently. They show us that the universe has built-in responses to extremes, that when pushed too far, reality does not shatter. It reorganizes. They are, in this sense, messages from the edge, silent signals that say, "Here is how far you can go." As this chapter comes to a gentle close, one thought remains suspended in the quiet. If black holes mark the limits of space-time under extreme density, what happens at even smaller scales, where space itself begins to lose meaning altogether? Part 7. The smallest scale of all. If you could keep zooming inward past atoms and quarks, you would eventually reach a scale where space itself begins to flicker. This is the Planck scale, a realm so small that distances lose their meaning. Here, energy fluctuations are so intense that space-time behaves more like foam than fabric. It is at this boundary that scientists suspect space becomes unstable, vulnerable to forces we do not yet fully understand. To imagine this descent, begin gently. Picture the familiar world shrinking away. Molecules dissolve into atoms. Atoms unravel into electrons and nuclei. Nuclei reveal protons and neutrons. Those, in turn, give way to quarks and gluons, flickering in confined motion. Each step inward feels dramatic, yet physics remains confident. The rules are strange, but they still hold. Then, at a scale far smaller than anything we can directly observe, confidence fades. The Planck scale is not just small, it is unimaginably small. About 1/10 million trillion trillionth of a meter, a length so tiny that even if you magnified a proton to the size of the observable universe, the Planck length would still be smaller than a grain of sand in comparison. At this scale, our best theories stop agreeing with one another. General relativity, which so beautifully describes gravity and space-time on large scales, assumes a smooth, continuous geometry. Quantum mechanics, which governs particles and fields, thrives on uncertainty, probability, and fluctuation. At the Planck scale, both must apply at once, and when they do, the picture fractures. Energy fluctuations become unavoidable here. According to quantum mechanics, confining energy to such a small region makes its uncertainty enormous. Energy spikes and drops violently, but energy curves space-time. So space-time itself becomes unstable, jittering and warping under the strain. This is where the idea of spacetime foam arises. Physicist John Wheeler described spacetime at the Planck scale as a seething foam of microscopic black holes and wormholes, constantly forming and dissolving. Not literal holes you could fall into, but fleeting distortions in geometry, space bubbles, time shimmers. The very notion of a fixed distance evaporates. At this scale, asking how far apart 2 points are may no longer make sense. The points themselves are uncertain. Space does not sit still long enough to be measured. Time may not flow smoothly from one moment to the next. Cause and effect blur. This does not mean reality becomes chaotic in the everyday sense. It means that our familiar concepts stop applying. Smoothness is an emergent property, not a fundamental one. Just as temperature only makes sense when many particles are involved, spacetime may only make sense when viewed from far enough away. From this perspective, the calm fabric of spacetime you inhabit now is an average, a large-scale illusion that arises when countless Planck-scale fluctuations cancel out. Beneath it, at the smallest scales, reality is restless. What makes the Planck scale so significant is that it represents a boundary not just of size, but of knowledge. To probe smaller distances, you would need higher and higher energy, but energy itself curves spacetime. At some point, trying to look closer would collapse the region you are examining into a tiny black hole, hiding the very information you sought. In this way, nature enforces a limit. Below the Planck length, the idea of distance may be meaningless, not because it is forbidden, but because it cannot be operationally defined. You cannot measure what cannot exist independently of the act of measurement. This suggests that space itself may be quantized, composed of discrete units rather than a continuous whole. Some theories propose tiny loops of spacetime, others vibrating strings, others networks of relationships more abstract than geometry. None have yet been confirmed. But all agree on one thing. The Planck scale marks the edge of spacetime as we know it. Here, the danger to space is not collapse under gravity alone, but dissolution under uncertainty. Energy fluctuations do not gently curve space, they shake it, stretch it, tear at its continuity. Spacetime survives only as a statistical structure, an average over chaos. This realization reframes the idea of destruction. Space does not break because it is weak. It breaks because it is not fundamental. It emerges from deeper rules that reveal themselves only when pushed to extremes. In the early universe, conditions near the Planck scale were universal. All of space was once compressed into this regime. The laws we know had not yet separated. Gravity, electromagnetism, and the nuclear forces may have been unified. Spacetime itself may have been a transient phase, cooling into existence as the universe expanded. As expansion continued, energy densities dropped, fluctuations calmed, space smoothed, time found direction. The universe crossed a threshold from foam to fabric, from instability to structure. In this sense, spacetime has already survived its most dangerous moment. Today, the Planck scale remains far beyond experimental reach. Even our most powerful particle accelerators fall short by many orders of magnitude. To recreate such conditions would require energies comparable to those present just after the Big Bang. Nature has locked this realm behind cosmic barriers. Yet, its influence remains. Black hole horizons, the entropy of spacetime, the limits of information storage, all hint at Planck-scale physics beneath the surface. Even the smooth expansion driven by vacuum energy may ultimately be rooted in phenomena at this smallest scale. For you, listening now, the Planck scale feels impossibly distant, and yet, it is not elsewhere. It is everywhere. Every point in space carries this restless potential beneath its calm exterior. The floor beneath you, the air around you, the stars overhead, all rest upon this same foundation. The universe feels solid because you exist far from its limits. There is something deeply soothing in that realization. The most violent uncertainties of reality are confined to scales so small they never intrude on daily life. Space holds together where it needs to. It becomes strange only where nothing familiar could survive anyway. The Planck scale reminds us that reality is layered, that what feels fundamental may only be provisional, and that beneath even the most stable structures lies a deeper, quieter mystery. As this chapter draws to a close, one question remains suspended, delicate and unresolved. If spacetime itself dissolves at the smallest scales, what happens when energy pushes not inward, but outward, testing the limits of space on the largest scales of all? Part 8. Can energy tear space apart? There are theoretical energies so vast that they could do more than bend space. Some equations suggest they could rip it open, creating defects or tears in spacetime itself. These hypothetical events would not resemble explosions, but sudden topological changes, where space rearranges its own structure. Such ideas remain speculative, yet they arise naturally from extending known physics to its extremes. When we imagine space being torn, our minds often reach for violent imagery. Rips, cracks, cosmic ruptures spreading outward like shock waves. But physics does not describe it this way. If spacetime were ever to tear, it would not scream or shatter. It would quietly change its rules. Geometry itself would shift, and reality would continue under a different set of relationships. To understand this possibility, it helps to remember that space is not merely distance, it has structure, topology, rules about how regions connect, loop, and relate to one another. Most of the time, that structure is simple. Space is continuous. Paths can be smoothly deformed. A circle can shrink to a point. Nothing exotic occurs. But at extreme energies, topology may no longer remain fixed. In mathematics and physics, a topological change is not about stretching or bending, but about connectivity. It is the difference between a surface with no holes and one with a hole, between a line and a loop, between separate regions and a single connected whole. These changes are usually forbidden in smooth spacetime. The rules of general relativity strongly resist them, unless energy intervenes. Some theoretical models suggest that if energy density becomes high enough in a localized region, spacetime could undergo a topological transition, not by tearing like fabric, but by reconnecting differently. A new boundary could form, a region could pinch off, two distant points could become linked, or a once continuous region could separate. These ideas emerge most naturally in attempts to unify gravity with quantum mechanics. At the Planck scale, spacetime already behaves unpredictably. If such fluctuations were amplified by enormous energy, they might stabilize into permanent defects. Physicists call these hypothetical structures spacetime defects. Examples include cosmic strings, domain walls, and other topological remnants that may have formed in the early universe as it cooled and expanded. These are not rips in space, but frozen irregularities in its structure, like wrinkles locked into the fabric of reality. Cosmic strings, for instance, are predicted by some theories to be incredibly thin, incredibly dense lines of energy stretching across vast distances. They would not pull objects toward them in the usual way. Instead, they would alter the geometry around them, causing space to be slightly conical. Traveling around, one would feel strange, as if a slice of space were missing. No such objects have been conclusively observed, but their possibility shows that spacetime can host imperfections without collapsing entirely. More speculative still is the idea that spacetime could tear and reconnect in ways that isolate regions of the universe. A pocket of space could detach, forming what some theories describe as a baby universe. The parent spacetime would remain intact, while the new region evolves independently, carrying away energy and information. This would not be an explosion. From the outside, it might look like a black hole forming. From the inside, it might feel like a new beginning. Space would not be destroyed, it would be repurposed. These ideas feel abstract because they are. They sit at the edge of what mathematics allows and what experiments can test. But they are not invented at random. They arise when physicists ask consistent questions about what happens if energy continues to increase beyond known thresholds. General relativity allows spacetime to curve arbitrarily. Quantum mechanics allows energy fluctuations to grow at small scales. When both are pushed together, topology becomes flexible. The key idea is this: space may not be infinitely elastic. There may be limits not just to how much it can bend, but to how it can remain connected. Past a certain point, maintaining continuity may cost more energy than changing structure. In such a scenario, spacetime does not tear because it is weak. It tears because it is economical. The universe chooses the configuration that satisfies its laws with the least resistance. This reframes the fear entirely. The universe does not catastrophically fail. It calmly transitions. It is also important to note how unreachable these energies are. Theoretical estimates place them far beyond anything that could occur naturally today, except perhaps in the most extreme environments imaginable. Not even black holes are expected to produce the kind of conditions required to stabilize spacetime tears. These events, if they occur at all, would most likely belong to the earliest moments of the universe, when energy densities were immense and spacetime itself was young and malleable. In that era, symmetry breaking may have left behind subtle scars, regions where the structure of space is slightly different. Most would be harmless. Some might influence the motion of matter in gentle, measurable ways. Others may have vanished long ago as the universe smoothed itself out. Modern observations suggest that if spacetime defects exist, they are rare and weak. The universe we observe is remarkably uniform. Space connects cleanly. Geometry behaves predictably. Whatever tearing may have been possible in the past, it did not dominate the outcome. This again points to a recurring theme. Nature allows extremes, but does not favor them. Stability emerges, irregularities fade. The universe finds calm configurations and remains there for vast stretches of time. Even dark energy, which stretches space itself, does not tear it. Expansion increases distance, not disconnection. Space grows, but its structure remains intact. From your perspective, resting now, this means that space around you is not fragile. It is not on the verge of ripping open. The conditions required for such transitions are unimaginably far removed from daily existence. The same laws that permit these theoretical possibilities also ensure your safety from them. And yet, contemplating them serves a purpose. They remind us that space is not an immutable backdrop. It has a life cycle, a history, a range of behaviors that extend far beyond intuition. They also hint at something deeper. That space may be one phase of something more fundamental, a state that can change, transition, or give way under certain conditions. Just as water can freeze or boil, spacetime may have phases we have barely glimpsed. In this view, tearing space apart is not destruction, it is transformation, and transformation does not imply danger. It implies continuity under change. As you breathe slowly, the geometry around you remains gentle and reliable. The paths through space are open. Time flows forward. Connectivity holds. The universe is in one of its long, quiet phases, where extremes are rare and calm dominates. These speculative ideas live at the far edges of physics, where mathematics stretches beyond evidence. They are not predictions of imminent events, but explorations of possibility, thought experiments that test the resilience of reality. And in doing so, they reveal something comforting. Even when pushed to its limits, the universe responds with structure, not chaos, with rules, not randomness. As this chapter settles, another question rises softly into awareness. If space can change its structure under extreme energy, what protects the universe from such transitions happening everywhere at once? Part 9. False vacuums and silent catastrophe. One of the most unsettling ideas in modern cosmology is that our universe may exist in a temporary, unstable state known as a false vacuum. If a lower energy state exists, space could one day transition to it. This would not arrive with warning or sound. A bubble of new physics would expand at the speed of light, rewriting the laws of reality as it passed. Space would not burn, it would simply become something else. To understand this idea, it helps to first let go of how the word vacuum is used in everyday language. In physics, a vacuum is not merely empty space, it is a state of energy. And like all energy states, it can have different levels, some more stable than others. Imagine a landscape of hills and valleys. A ball resting at the very bottom of the deepest valley is stable. It has nowhere lower to go. But a ball resting in a shallow dip halfway down a hill may appear stable, even though a deeper valley exists nearby. That shallow dip is a false minimum. The ball can remain there for a very long time, but it is not in the lowest possible state. A false vacuum is like that shallow valley. Our universe may currently reside in such a state, balanced in a configuration that is stable for now, but not absolutely stable forever. The energy of empty space may not be at its lowest possible value. And if that is true, then a deeper, more stable vacuum state could exist. This idea arises naturally from quantum field theory, the framework that describes how particles and forces emerge from underlying fields that fill all of space. These fields can settle into different configurations, each corresponding to a different vacuum state. Some configurations are stable, others are metastable, long-lived but ultimately temporary. What makes this unsettling is not that such a transition is likely, but that it is possible in principle. If a transition were to occur, it would not behave like anything familiar. There would be no explosion, no shockwave, no sound. Instead, a tiny region of space would randomly tunnel into the lower energy state. This region would form a bubble, a boundary separating the old vacuum from the new. Inside the bubble, the laws of physics could be different. The values of fundamental constants might change. Particle masses could shift. Forces could strengthen or weaken. Atoms as we know them might no longer be stable. Chemistry might become impossible. Space and time would still exist, but the rules governing them would be rewritten. The bubble would expand outward at the speed of light. There would be no way to see it coming. No warning signal could outrun it. From the inside, there would be no experience at all. One moment, space would be as it has always been. The next, it would be something else entirely. This is why physicists sometimes refer to false vacuum decay as a silent catastrophe. Not because it is violent, but because it is absolute. It does not destroy structures. It replaces the framework that allows structures to exist. Yet, despite how dramatic this sounds, it is important to place it in context. False vacuum decay is not a prediction. It is a possibility allowed by certain theories. And those theories also suggest that if our vacuum is metastable, it is extraordinarily long-lived, longer than the current age of the universe by many orders of magnitude. In other words, if this transition is possible at all, it is not something to fear on human timescales. The mathematics behind this idea comes from the same quantum principles that allow particles to tunnel through barriers. Even if a system lacks enough energy to cross a barrier classically, quantum mechanics allows a small probability of passing through anyway. Applied to the vacuum, this means that even if the universe is stable, there's a tiny chance it could transition to a lower energy state. Tiny, in this context, means unimaginably small. The universe has existed for nearly 14 billion years without such an event occurring, at least within our observable region. That longevity itself is evidence of extraordinary stability. The false vacuum, if it is false at all, is remarkably patient. Some measurements, particularly those involving the Higgs field, suggest that our vacuum may indeed be metastable rather than perfectly stable. But metastable does not mean fragile. It means balanced in a way that allows vast stretches of calm time. The universe is not perched on a knife edge. It is resting in a wide basin, even if a deeper one exists somewhere beyond reach. What is especially striking about this idea is how impersonal it is. False vacuum decay does not target stars or galaxies. It does not move through space like a wave of destruction. It simply changes what space is. There is no malice, no drama, only a shift in configuration. And this reflects a broader theme in physics. The universe rarely ends things loudly. Its most profound changes often happen quietly, guided by energy minimization and mathematical consistency rather than violence. Even the Big Bang, often imagined as a tremendous explosion, was not an explosion in space. It was a change of space, an expansion of geometry, a transformation of state. False vacuum decay, if it ever occurred, would be another transformation of that kind. There is also a sense in which this possibility is deeply theoretical. We have no direct evidence that a lower energy vacuum state exists. We have no measurements that tell us what the laws of physics would look like inside such a bubble. And we have no way to observe regions of the universe where this might have already happened, if such regions exist at all. Physics allows the idea. Nature has not confirmed it. And even if the idea were true, the universe has mechanisms that favor stability. Expansion dilutes energy. Fields settle into configurations that resist change. Quantum tunneling probabilities decrease dramatically with scale. The larger and more complex a system becomes, the harder it is to reorganize completely. In that sense, the calm you experience now is not an illusion. It is the natural outcome of a universe that has found a long-lasting balance. The false vacuum concept is unsettling only if taken out of proportion. In context, it becomes something else. A reminder that even the deepest structures of reality may not be final, that the universe is not frozen into one configuration forever. And yet, it also reminds us how extraordinarily resilient our current state has been. For billions of years, the laws of physics have remained consistent enough to allow stars to shine steadily, galaxies to form gracefully, and life to emerge. That consistency is not trivial. It is the product of a vacuum state that, whether truly stable or not, has proven itself remarkably accommodating. As you rest now, space around you is not waiting to change. It is not trembling on the brink of transition. It is settled, calm, and deeply familiar. The same vacuum energy that fills all of space presses evenly in every direction, maintaining the structure you inhabit. There is comfort in knowing that the most dramatic possibilities in physics are also the most distant, that the universe, while capable of profound change, prefers long periods of quiet continuity. False vacuums remind us that reality may have layers beyond what we experience, that what feels permanent may only be provisional on cosmic timescales. But they also remind us that the present moment is supported by deep, enduring stability. And as this quiet chapter draws to a close, one more question emerges, gentle and unhurried. If the universe itself can change state without warning, what keeps such transitions so rare and stability so common across the vastness of space and time? Part 10. Energy beyond human scale. The energies capable of threatening spacetime are far beyond anything humanity could create. They belong to the early universe, to cosmic inflation, and to processes that unfolded fractions of a second after time began. Thinking about them is not an exercise in fear, but in perspective. These forces remind us how gentle our corner of the cosmos truly is. When we speak of extreme energy, it is tempting to think in terms of our own achievements. Nuclear reactions, particle accelerators, the brightest flashes humanity has ever produced. But even the most powerful technologies we possess barely register on the scale that matters to spacetime itself. They are whispers compared to the forces that shaped the universe in its infancy. To appreciate this difference, it helps to imagine the early universe not as a place filled with objects, but as energy itself. In the first moments after the Big Bang, there were no stars, no atoms, no particles with stable identities. There was only an intense, seething field of energy packed into an unimaginably small volume. Temperatures and densities were so high that the familiar distinctions between forces had not yet emerged. Gravity, electromagnetism, and the nuclear forces may have been unified into a single interaction. Spacetime itself was young, flexible, and profoundly energetic. Curvature was extreme everywhere. Quantum fluctuations were not rare events, but the dominant feature of reality. This was the era when energy truly ruled geometry. One of the most dramatic chapters in this early history is cosmic inflation. According to inflationary theory, the universe underwent a brief period of exponential expansion, driven by a high-energy vacuum-like state. In a tiny fraction of a second, space expanded by an enormous factor, smoothing out irregularities and stretching quantum fluctuations across cosmic scales. The energy involved in inflation dwarfs anything we can imagine producing today. It reshaped spacetime itself, not locally, but everywhere at once. Regions that were once close became separated by vast distances. The universe's large-scale structure was set, During this fleeting moment, and yet even this extraordinary event was not violent in the usual sense. There was no blast wave traveling through space. Space itself expanded. Energy did not tear space-time apart. It guided it into a new phase. After inflation ended, that immense energy was released into particles and radiation. The universe reheated. Forces separated. Space-time relaxed into a calmer geometry. The extreme conditions faded, leaving behind a universe capable of forming structure. This transition is crucial. It shows that even the most overwhelming energies known to physics did not destroy space-time. They transformed it, then receded. As the universe expanded and cooled, energy density dropped rapidly. Within seconds, then minutes, then years, conditions softened enough for protons and neutrons to form, then atoms, then stars. The universe moved steadily away from its most dangerous regime. From that point on, the energies required to seriously threaten spacetime became increasingly rare. Today, the most extreme environments we know are found near black holes and in the hearts of neutron stars. Even there, the energy densities, while immense, are localized. Spacetime bends sharply, but the universe contains and isolates these regions. The rest of space remains calm. Human technology does not come close. The Large Hadron Collider, the most powerful particle accelerator ever built, can probe energies of trillions of electron volts. That sounds enormous, and on human scales, it is. But compared to the Planck energy, the scale at which spacetime itself becomes unstable, it is vanishingly small. More than 15 orders of magnitude smaller. Even if we covered the entire planet in accelerators, even if we harnessed the output of the sun for centuries, we would not approach the energies that shaped the early universe. Nature has placed these regimes far beyond reach. This is not a limitation of ingenuity. It is a feature of reality. The energies that threaten spacetime are not meant to be accessed casually. They belong to the universe's formative moments, when everything was compressed, unified, and fluid. As the cosmos matured, those conditions became inaccessible, locked behind expansion and cooling. This separation is comforting. It means that the calm structure you inhabit is not fragile. It is not one experiment away from collapse. The laws of physics that allow extreme possibilities also protect you from them by making them extraordinarily difficult to achieve. There is a tendency, when discussing cosmic extremes, to imagine danger lurking everywhere, but the opposite is true. The universe is mostly gentle. Vast regions of space are cold, empty, and stable. Energy is spread thin. Geometry is nearly flat. Change happens slowly. Even cosmic disasters like supernovae are localized. They release tremendous energy, but that energy disperses quickly into space. It does not accumulate. It does not threaten spacetime on a global scale. Perspective is key here. When physicists study energies beyond human scale, they are not uncovering imminent threats. They are mapping boundaries, asking how reality behaves under conditions that no longer exist and may never exist again within our observable universe. These studies tell us where spacetime's limits lie, not because we are close to crossing them, but because understanding limits deepens our appreciation of stability. The fact that spacetime can be threatened at all is remarkable. The fact that it usually is not is even more so. There's also something humbling in realizing how small our influence is on the grand structure of reality. Human activity can change ecosystems, climates, and even the surface of a planet. But spacetime itself remains indifferent. Its geometry is shaped by stars, galaxies, and the accumulated energy of the cosmos, not by our machines. This is not to diminish human achievement, it is to place it gently in context. We live in a universe that has already passed through its most volatile phase. What remains is a long, cooling aftermath, a gradual unfolding toward greater calm. The energy densities that once threatened to overwhelm spacetime are gone, diluted by expansion. Dark energy now dominates, but it acts slowly and uniformly. It stretches space but does not tear it. It changes the future gently, over trillions of years. In this light, the idea of energy destroying space becomes less alarming and more instructive. It tells us that reality has phases, that what is possible depends on when and where you are in cosmic history. You are here, now, in a remarkably peaceful era. As you rest, the universe around you is stable enough to support long-lived stars, complex chemistry, and quiet nights. That stability is not accidental. It is the result of energy falling far below dangerous thresholds, and that is perhaps the most important takeaway of all. The same physics that allows spacetime to bend, break, or change under extreme energy also ensures that such conditions are rare and fleeting. The universe does not linger in danger. It passes through it quickly and moves on. Energy beyond human scale belongs to the universe's youth, not its maturity. So when you hear about these immense forces, let them inspire awe rather than concern. They are reminders of where the universe came from, not warnings of where it is headed anytime soon. The cosmos has settled into a gentle rhythm, one that allows time to pass quietly, space to hold steady, and minds like yours to wonder without fear. And as we continue this calm journey, another question begins to take shape. If spacetime has survived its most extreme energies already, what ensures that it remains stable for the unimaginably long future still ahead? Part 11. Why space usually survives. Despite all this potential for destruction, space is remarkably stable. The universe naturally spreads energy out, cooling and smoothing itself over time. Expansion acts as a release valve, preventing dangerous concentrations from forming easily. This balance between gravity and expansion has kept spacetime intact for nearly 14 billion years, allowing complexity, structure, and life to emerge. At first glance, this stability seems almost surprising. We have seen how energy can bend space, how density can collapse it, how extreme conditions can push spacetime toward its limits. And yet, when you look around, space feels calm. Distances remain reliable. Time flows gently forward. The universe has not torn itself apart, despite having had countless opportunities to do so. The reason lies in a quiet tendency built into nature itself. Energy prefers to spread. From the moment the universe began expanding, energy density started to fall. What was once compressed into a tiny region was quickly diluted across an ever-growing volume. This dilution is not incidental. It is one of the most powerful stabilizing forces in existence. As space expands, energy thins out, reducing curvature and easing the strain on spacetime. Expansion is not something happening within space. It is something space itself is doing, and in doing so, it continuously lowers the risk of dangerous concentrations forming. Gravity works in the opposite direction. It pulls matter and energy together, encouraging clumping. Stars form, galaxies gather, black holes emerge, but gravity operates locally, while expansion operates globally. Gravity can win in small regions, but expansion dominates on the largest scales. This division of influence is crucial. Where gravity pulls matter inward, expansion stretches space outward. The universe finds a balance between these two tendencies. Structures can form without the entire cosmos collapsing. Density can rise locally without threatening spacetime everywhere. Even when gravity wins decisively, as in black hole formation, the consequences are contained. Event horizons isolate extreme curvature. The rest of spacetime remains undisturbed. Collapse does not propagate outward unchecked. This containment is not an added feature. It is an inherent property of spacetime geometry. Another stabilizing factor is the way energy transforms. High-energy states tend to decay into lower-energy ones. Excited fields settle. Particles lose energy through radiation. Systems move toward equilibrium. This relentless drift toward lower-energy configurations keeps spacetime from lingering near dangerous thresholds. The early universe is a perfect example. It began in a state of extraordinary energy density, but it did not stay there. Expansion and cooling rapidly transformed that energy into radiation, then into matter, then into structure. Each step reduced overall density and softened curvature. What could have been catastrophic was instead transitional. There is also a subtle but important role played by symmetry. Many of the universe's most extreme behaviors arise when symmetries are broken. Forces separate. Fields settle into particular states. But once broken, these symmetries tend to remain stable. The laws governing spacetime become consistent across vast regions, reducing the likelihood of sudden global transitions. In this way, the universe locks itself into long-lasting phases. The vacuum state we discussed earlier is part of this stability. Whether truly stable or merely metastable, it has persisted for billions of years. That persistence matters. It means that the energy landscape of the universe has wide, flat regions where change is slow and unlikely. Think of spacetime as resting in a broad basin rather than balancing on a peak. Small disturbances do not push it into a new state. It takes extraordinary conditions to do so. Entropy also plays a role. As the universe evolves, entropy increases. Energy becomes more evenly distributed. Temperature differences shrink. Sharp gradients fade. High-entropy states are smoother, quieter, and less prone to dramatic change. Spacetime in this sense grows calmer with age. This does not mean nothing happens. Stars still burn, galaxies still collide, black holes still grow, but these events occur against a backdrop of increasing uniformity. They are local ripples, not global threats. Even dark energy, which drives accelerated expansion, contributes to stability in an unexpected way. By stretching space ever faster, it further suppresses the formation of new large-scale structures. Matter becomes more isolated. Energy concentrations become harder to form. The universe drifts toward a quieter future. There is an irony here. Expansion, which might sound like a disruptive force, actually protects spacetime from collapse. It ensures that extreme densities become rarer, not more common. It gently pulls the universe away from its most dangerous configurations. From a human perspective, this is deeply reassuring. The floor beneath you is not floating on the edge of a cosmic rupture. The space around you is not fragile. It is the product of a long history of self-regulation, of forces that counterbalance one another across scales far beyond intuition. Even the most violent events you hear about in astronomy are tiny compared to the universe as a whole. A supernova releases enormous energy, but that energy disperses quickly into space. A black hole traps extreme curvature, but only within a confined region. The cosmos absorbs these events without strain. This resilience is not accidental. It is written into the equations that govern spacetime. General relativity allows curvature, but it also predicts horizons that limit its spread. Quantum mechanics allows fluctuations, but it also enforces uncertainty that prevents infinite precision. Together, these frameworks constrain how extreme reality can become. Space survives because it has options. When pushed in one direction, it expands. When pulled inward, it curves and isolates. When energy spikes locally, it disperses globally. When instability threatens, it transitions into a new configuration that restores balance. Destruction, in the absolute sense, is rare. Transformation is preferred. This perspective changes how we think about cosmic danger. The universe is not constantly flirting with collapse. It is actively maintaining equilibrium. Extremes occur, but they are managed. Boundaries form. Phases change. Stability returns. As you lie still now, this stability is all around you. Space holds its shape. Time flows smoothly. The same laws that allow for cosmic extremes are the ones keeping everything calm here. There is something profoundly peaceful in knowing that the universe is not brittle, that it has endured conditions far more intense than anything that exists today, that it has already passed through its most perilous chapters and emerged into a long, gentle era. Space usually survives because it knows how to let go of excess. It releases energy, it expands, it cools, it smooths, and perhaps most importantly, it does not rush. Cosmic time is patient. Processes unfold over billions of years. Changes happen slowly enough that stability is preserved. Even the future transformations driven by dark energy will take trillions of years to fully manifest. Nothing sudden, nothing violent, just gradual evolution. As this chapter comes to rest, one final thought settles quietly into place. If space survives because it spreads energy and avoids extremes, what role does time itself play in protecting the universe from its own limits? Part 12. The quiet role of dark energy. Dark energy fills space uniformly and drives the universe's accelerating expansion. It is not destructive in the way explosions are, but it quietly stretches space-time itself. Over unimaginably long timescales, this stretching may isolate galaxies, thin out matter, and change how energy behaves. Destruction here is not sudden, but slow and gentle, unfolding over trillions of years. Dark energy is one of the most subtle forces ever discovered. You cannot see it. You cannot touch it. It does not clump into objects or shine with light. And yet, it dominates the future of the universe. Its presence is inferred not through spectacle, but through patience, through careful measurements of distant galaxies drifting apart faster than expected. At first, this acceleration came as a surprise. Gravity should slow cosmic expansion, not speed it up. Matter pulls inward, structure forms. The universe should gradually ease into stillness. But observations told a different story. Space itself is stretching faster with time, as if something embedded within it is gently pushing everything apart. That something is dark energy. Unlike matter or radiation, dark energy does not dilute as space expands. As the universe grows larger, the total amount of dark energy grows with it because it is tied to space itself. This creates a quiet feedback loop. More space means more dark energy. More dark energy means faster expansion. Faster expansion creates even more space. Yet this process is astonishingly calm. On human scales, dark energy is imperceptible. The distances between atoms do not grow. Molecules remain intact. Gravity and electromagnetic forces easily overpower the gentle stretching of spacetime. Even galaxies remain bound for billions of years, their stars continuing to orbit as if nothing has changed. Dark energy works only on the largest scales, where gravity grows weak and distances become vast. Over time, however, its influence accumulates. Galaxies that are not gravitationally bound to one another drift farther apart. Clusters separate. Light from distant regions stretches until it fades into invisibility. The observable universe slowly shrinks, not because space collapses, but because more of it slips beyond reach. This is not destruction in the dramatic sense. Nothing breaks apart violently. Instead, connections quietly dissolve. In the far future, galaxies outside our local group will disappear from view. Not because they cease to exist, but because space between us grows too quickly for their light to ever arrive. The universe becomes darker, emptier, and quieter, one horizon at a time. What makes this especially striking is how gentle the process is. Dark energy does not rush. It does not overwhelm gravity suddenly. It allows stars to form, burn, and die. It allows planets to settle into long, stable orbits. It allows life, wherever it arises, to have time. This slowness is not accidental. It reflects the small but persistent value of dark energy, strong enough to shape the universe's destiny, yet weak enough to allow complexity to flourish first. Over trillions of years, this stretching will thin out matter. Star formation will slow as galaxies lose the raw material needed to create new suns. Existing stars will fade. Black holes will dominate the remaining structure, quietly orbiting in an ever-expanding sea of space. Eventually, even these structures may feel the effects. As expansion continues, interactions become rarer, energy becomes harder to concentrate. The universe drifts toward a state sometimes called heat death, where everything is spread thin and gradients vanish. Yet even this end state is not violent. There is no moment when space-time tears or collapses, no final explosion, just an endless gentle unfolding. Space continues to stretch, time continues to pass. Change slows until it nearly stops. Dark energy, in this sense, is not a destroyer. It is a dissolver. It does not break structures. It slowly removes the conditions that allow new ones to form. This is why dark energy is often misunderstood. It sounds ominous, as though something is actively working against the universe. But dark energy is simply a property of space itself, a quiet tendency embedded in the fabric of reality. Some theories suggest dark energy is truly constant, a fixed feature of space-time known as the cosmological constant. Others suggest it may evolve slowly over time, changing its influence. Still others propose it as a sign of deeper physics yet to be understood. Regardless of its origin, its behavior remains calm and predictable. There is also an important distinction to make. Dark energy stretches space, but it does not increase energy density in a dangerous way. In fact, expansion lowers the density of matter and radiation, making extreme conditions less likely. In this way, dark energy contributes to the overall stability of spacetime. It pulls the universe away from collapse. Even in the distant future, when galaxies are isolated and stars are rare, spacetime remains intact. The stretching does not tear connections locally, it simply increases distance globally. From your perspective now, this future is so distant that it barely registers. Trillions of years stretch beyond imagination. Everything familiar exists on timescales far shorter than dark energy's ultimate influence. And that is the quiet comfort of it. Dark energy ensures that the universe changes slowly, that nothing sudden arrives, that the most profound transformations occur gently, over spans so vast they feel almost timeless. As you lie still, the expansion of space continues, but so slowly that even the most sensitive instruments struggle to measure it. The room around you is not growing. The planet beneath you is not stretching apart. The calm you feel is not threatened by cosmic forces. Dark energy operates on scales so large and times so long that it becomes almost philosophical rather than physical. It shapes the destiny of the universe without disturbing the present moment. In that way, it fits perfectly into the story we have been telling. The universe has many ways to handle excess energy in extreme conditions: collapse, horizons, quantum limits, and now, expansion, a gentle release that prevents density from building again. Dark energy is spacetime's long exhale. It is what allows the universe to age gracefully, drifting away from its dangerous youth into a quiet maturity. It ensures that the most intense chapters remain in the past, while the future unfolds softly. And as this chapter settles into stillness, one more question naturally arises. If space can stretch itself into calm emptiness, can it also heal, renew, or reorganize itself when pushed beyond its limits? Part 13. Could space heal itself? Some theories suggest that spacetime is more resilient than we imagine. Quantum gravity models hint that even when space breaks down at tiny scales, new structures emerge to replace it. Instead of tearing apart permanently, space may rearrange itself, preserving continuity in ways we have yet to observe. In this view, destruction and creation are two sides of the same quiet process. When we speak of space breaking, it is natural to imagine irreparable damage, a tear that cannot be undone, a collapse that ends all structure. But physics, especially at its deepest levels, often tells a gentler story. One where endings are not final and where breakdowns mark transitions rather than losses. At the heart of this idea is a simple question: is spacetime fundamental, or is it something that emerges from deeper rules? If spacetime is fundamental, then breaking it would indeed be catastrophic. But if spacetime is emergent, like temperature or pressure, then its breakdown might simply reveal a different layer of reality beneath it. In that case, what looks like destruction from one perspective could be reorganization from another. Quantum gravity theories explore exactly this possibility. These theories attempt to unify general relativity, which describes smooth spacetime, with quantum mechanics, which governs uncertainty and discreteness. While no single theory has yet been confirmed, many share a striking feature. Spacetime is not treated as a continuous fabric at the smallest scales. Instead, it is built from something more granular, more relational. In loop quantum gravity, for example, space is composed of tiny loops or networks. Areas and volumes come in discrete units, like pixels too small to see. When spacetime curvature becomes extreme, these loops do not collapse into infinities. They rearrange. Geometry changes phase. In this picture, singularities do not truly exist. Instead of infinite density, there is a smallest possible volume. Instead of collapse without end, there is a bounce. Spacetime reaches a limit, then transitions into a new configuration. The universe may have already experienced this. Some models suggest that the Big Bang was not the beginning of everything, but a transition from a previous phase. A contracting universe reaching a critical density, then rebounding into expansion. In this view, spacetime did not emerge from nothing. It healed itself by changing direction. Even black holes may follow a similar pattern. Inside a black hole, where classical physics predicts a singularity, quantum gravity may intervene. Extreme curvature could trigger a phase change in spacetime, preventing infinite collapse. The interior might evolve into a different region of spacetime entirely, perhaps connected to another universe or another epoch. From the outside, the black hole remains, the horizon stays in place, but internally, spacetime continues, reorganized rather than destroyed. This idea remains speculative, but it reflects a broader principle seen throughout physics. Nature dislikes infinities. When equations predict them, it is often a sign that a deeper description is needed. And the deeper description frequently restores finiteness through new structure. Healing in this sense does not mean returning to an original state. It means finding a stable configuration under new conditions. Think of how matter behaves. When compressed gently, it resists. When compressed further, it changes phase. Solid becomes liquid. Liquid becomes gas. Under extreme pressure, matter becomes plasma. Each transition looks like breakdown, but each is actually reorganization. Spacetime may behave the same way. At low energies, it appears smooth and continuous. At higher energies, it becomes flexible and curved. At extreme energies, it may become discrete, foamy, or relational. Each phase obeys different rules, but continuity is preserved across transitions. This possibility reframes our entire discussion. If space can heal itself, then even the most extreme events are not ends. They are passages, moments where one description gives way to another. This does not mean the universe is indestructible in a simple sense. It means that destruction is not absolute. Something always remains, even if it no longer resembles what came before. There is also growing evidence that information is preserved even through extreme processes. Black hole physics increasingly suggests that information is not lost, but encoded in subtle ways on horizons or in correlations we do not yet fully understand. If information survives, then continuity survives. And if continuity survives, then space itself may be more robust than our classical intuitions suggest. This resilience is deeply woven into the mathematical structure of physical law. Conservation principles, symmetries, invariances. These are not aesthetic choices. They are signs that nature prefers consistency over erasure. Even when forms change, relationships persist. From your perspective, resting now, this idea carries a quiet comfort. The universe is not brittle. It does not shatter irreversibly when stressed. It adapts. It reorganizes. It finds new ways to exist under new conditions. The calm space around you is one expression of that adaptability. It is spacetime in a low-energy, stable phase, smooth enough to support motion, light, and life. But beneath that calm lies a capacity for change that does not threaten continuity. This also suggests that the universe's future may not end in final emptiness or collapse. Even in scenarios where stars fade and galaxies drift apart, spacetime itself may continue, evolving slowly, finding new configurations beyond our current understanding. Healing does not require intention. It emerges naturally when systems obey rules that favor balance and continuity. And spacetime appears to be such a system. The most violent conditions we know, the Big Bang, black hole interiors, Planck scale fluctuations, all hint at transitions rather than terminations, at boundaries, not ends. This does not remove mystery, it deepens it. We do not yet know what spacetime becomes when it heals itself at the smallest scales. We do not know what lies beyond horizons or before expansion, but the patterns we see suggest persistence rather than annihilation. The universe has already survived its most intense moments, and it did so not by resisting change, but by embracing it. As you breathe slowly now, space around you is untroubled. It does not need to heal because it is not wounded. It is simply being itself in a phase where energy is low and geometry is gentle. But should that change? Should conditions one day push spacetime beyond familiar limits, the deeper rules of reality may quietly take over, guiding it into something new. Not broken, not erased, transformed. And as this chapter settles into stillness, another question rises softly, like a distant horizon coming into view. If space can heal and reorganize itself, what does that say about the ultimate fate of everything that exists within it? Part 14. Living inside a fragile balance. Every moment of calm you experience exists because energy, gravity, and expansion remain in balance. The fact that space holds together at all is a triumph of natural law. You live not on solid ground, but within a delicate equilibrium maintained across cosmic scales. This fragility is not something to fear, but something to quietly appreciate. When you sit or lie still, the world feels steady beneath you. Floors do not ripple. Walls do not drift apart. Time passes at a familiar pace. It is easy to assume that stability is the default state of reality. But from a cosmic perspective, stability is an achievement, not a given. It is something continuously maintained by competing influences that just happen here and now to be in harmony. Gravity pulls inward. It gathers matter, deepens curvature, and encourages collapse. Expansion pulls outward. It stretches space, lowers density, and prevents everything from falling together. Energy flows between these tendencies, sometimes amplifying one, sometimes softening the other. The universe exists in the tension between them. This balance is not static. It is dynamic, constantly adjusting as conditions change. Stars burn through fuel. Galaxies merge. Space expands. Energy spreads out. At every moment, the equations governing spacetime recalculate the shape of reality, and almost always, they arrive at something stable enough to continue. That is not trivial. If gravity were slightly stronger, the universe might have collapsed long ago. If expansion were stronger, matter might never have clumped into stars and galaxies. If energy behaved differently, spacetime might never have settled into a smooth geometry. The calm you experience is the result of parameters that sit within a narrow, life-permitting range. This does not imply design or intention, it implies sensitivity. The universe responds sharply to change, but it also possesses mechanisms that dampen extremes, feedback loops, horizons, phase transitions. These features keep reality from wandering too far from equilibrium. Even within your own body, you are an expression of balance. Forces pull atoms together while others push them apart. Energy flows through chemical reactions at just the right rates. Temperature, pressure, and structure coexist in a steady dance. None of this would be possible without the broader cosmic balance that makes stable matter possible in the first place. Zoom out, and the same pattern appears everywhere. Stars exist because gravitational collapse is halted by nuclear pressure. Too little pressure, and stars would implode. Too much, and they would never form. Galaxies persist because gravity binds them, while expansion stretches the space between them just slowly enough to allow long-lived structures. Even black holes, often imagined as ultimate destroyers, are part of this balance. They remove extreme density from surrounding space by sealing it off behind horizons. They prevent collapse from spreading. They act as safety valves, not failures. The universe does not eliminate imbalance by preventing it. It contains it. This is what makes the word fragile so subtle here. Fragility usually implies weakness, something easily broken, but cosmic fragility is different. It refers to sensitivity, not brittleness. The universe responds strongly to change, but it does not fall apart easily. Instead, it reorganizes. You are living inside a state that is neither rigid nor chaotic. It is poised, and that poise is what allows time to pass in a way that feels smooth, predictable, and safe. Consider how rare this is. For much of the universe's early history, conditions were too extreme for anything like this calm. Energy densities were high, geometry was restless, structures could not persist. Only after expansion cooled and smoothed spacetime did the balance settle into a long, gentle era. You exist during that era. This is not something the universe guarantees forever. Over trillions of years, dark energy will continue to stretch space. Star formation will slow, matter will thin, the balance will shift again toward a quieter, emptier state. But even that future is not violent. It is an evolution, not a collapse. Fragility, in this sense, does not mean imminent danger. It means dependency. The calm you experience depends on conditions remaining within certain bounds. And those bounds have held, remarkably, for nearly 14 billion years. There is something deeply grounding in that realization. The ground beneath you is not absolute. It is a momentary expression of cosmic conditions that happen right now to support stability. And they do so not grudgingly, but generously. The universe gives long stretches of calm between its transitions. This perspective changes how you relate to uncertainty. Knowing that stability is maintained rather than guaranteed does not make it feel less real. It makes it more precious. Each quiet moment exists because countless processes, from quantum fields to galactic motions, align just well enough. You are not standing on certainty. You are floating in balance. And balance does not require tension or strain. Most of the time, it feels like rest. Physics often reveals that the most enduring states are not those of absolute minimum energy, but those of dynamic equilibrium. Systems that can absorb disturbances, redistribute energy, and return to stability. Spacetime itself appears to be such a system. When energy concentrates, space curves and isolates it. When energy spreads, space expands and cools. When uncertainty grows, geometry becomes probabilistic. When certainty returns, smoothness emerges again. This adaptability is what allows fragility and resilience to coexist. It is also what allows life to exist without constant threat from cosmic extremes. The universe does not frequently test its own limits. It spends most of its time far from them. That is why the most dramatic scenarios in physics feel distant. They belong to edges, beginnings, and ends, not to the broad middle where you reside. Living inside a fragile balance does not mean living in danger. It means living in a state that depends on harmony rather than force, on cooperation between laws rather than dominance of one. This harmony extends to time itself. Time flows forward because entropy increases gently, not because it surges. The arrow of time exists because energy gradients are shallow enough to be navigated slowly. Everything about your experience of reality depends on moderation, and moderation, in a universe capable of extremes, is extraordinary. As you rest now, nothing is demanding immediate change. Space holds, time flows, energy dissipates quietly. The balance continues without effort because it has learned how to sustain itself. This is not guaranteed forever, but it does not need to be. It is guaranteed for now. And now is all experience ever requires. Understanding the fragility of this balance does not undermine it. It deepens appreciation. It turns ordinary calm into something quietly miraculous. You are not insulated from the universe. You are carried by it. And as this chapter draws to a gentle close, one final question emerges, soft and unhurried. If living inside this balance is what makes existence possible, what does it mean to rest within it, knowing it is temporary, yet enduring? Part 15. The Energy That Never Came. Perhaps the most comforting thought is this: the energies capable of destroying space itself belong mostly to the past. They shaped the early universe, then faded as space expanded and cooled. What remains is a gentler cosmos, one where the same laws that allow destruction also allow stability, rhythm, and rest. And in that balance, space continues to hold you, silently and reliably, as it always has. There is a quiet mercy written into the history of the universe. The most extreme energies, the ones that could bend space-time beyond recognition, arrived early and did their work quickly. They carved the initial shape of reality, set the conditions for expansion, and then receded, leaving behind a universe no longer dominated by intensity, but by endurance. In the earliest moments after the beginning of time, energy ruled everything. Space was dense, restless, and fragile. Forces were unified. Geometry was unstable. The universe existed in a state where change happened faster than structure could form. This was not a place where calm could exist only transition. And yet, that era did not last. As space expanded, energy thinned, temperatures dropped, symmetries broke, forces separated, space-time relaxed. The universe moved away from its most dangerous thresholds, not reluctantly, but naturally. Expansion acted as a cooling breath, carrying excess energy outward and away. The energies that could have torn space apart were diluted by distance and time. What followed was not emptiness, but opportunity. With energy no longer overwhelming geometry, space could settle into smoothness. Time could flow steadily, matter could clump gently rather than collapse violently. The universe entered a long, patient phase, one defined not by extremes but by persistence. Stars formed, galaxies assembled, heavy elements were forged, complexity emerged. All of this required a universe that had already passed through its most volatile stage. When physicists imagine scenarios where space-time might be destroyed, they are often describing conditions that resemble those early moments. Energy densities approaching the Planck scale, vacuum states far removed from equilibrium, topological transitions that require immense concentration of power. These are not conditions the modern universe easily produces. Today, energy is spread thin across vast expanses of space. Even the most energetic events, supernovae, gamma-ray bursts, black hole mergers, are local and fleeting. Their power dissipates quickly. They do not accumulate. They do not threaten the global structure of space-time. The universe has grown too large, too diffuse, for such dangers to arise again easily. This is not an accident. It is a consequence of expansion. As space grows, it becomes harder and harder to concentrate energy enough to challenge its structure. Nature has built a kind of safety into scale itself. Distance becomes protection, size becomes stability. In this sense, the universe has aged out of its dangerous youth. What remains is a cosmos governed by the same laws, but operating far from their breaking points. Gravity still curves space, energy still influences geometry, but the conditions required to push those relationships into instability are no longer common. Even dark energy, which dominates the universe today, does not threaten space-time in the way early energies did. It stretches space, but it does so gently, uniformly. Without creating dangerous concentrations, it guides the universe toward a quiet, expansive future rather than a violent one. This gives the present moment a special quality. You exist in a universe that has already survived its most extreme possibilities. The energy that could have destroyed space has already done what it needed to do, shaping the cosmos, then fading into the background. What remains is a long era of relative calm. That calm is not permanent, but it is durable. Trillions of years may pass before the universe reaches another major transition. And even then, that transition is expected to be slow, diffuse, and gentle. Not an ending, but a thinning. Not destruction, but quiet. Change. There is something deeply reassuring in this perspective. It means that the space around you is not under threat. It is not holding together by force. It is resting in a configuration that has proven itself stable over nearly 14 billion years. The same space-time that once endured unimaginable energy now supports stillness with ease. You are not living near the edge of cosmic danger. You are living in the wide middle, where the universe has room to breathe. The energy that never came, the energy that could have torn space apart but did not, reminds us that possibility does not equal inevitability. Physics allows many things that nature never chooses. The universe explores only a small subset of what is mathematically permitted, and what it has chosen, so far, favors longevity. This does not diminish the wonder of extreme physics. It enhances it. The fact that space-time can break under certain conditions makes its stability more remarkable, not less. The calm you feel is not trivial. It is earned through cosmic history. Space is not strong because it cannot fail. It is strong because it rarely needs to be tested. As you rest now, space is doing what it has done for billions of years, holding distances steady, allowing light to travel, letting time pass in an orderly way. It does this not because it is rigid, but because it is balanced. The early universe was a storm of energy. The present universe is a slow tide, and you are floating in it, supported not by force, but by harmony. This is why the idea of space being destroyed, while fascinating, ultimately leads back to comfort. It reminds us that destruction requires extraordinary conditions, conditions that once existed, briefly, long ago, conditions that shaped everything, then withdrew. What remains is a cosmos that has learned how to persist. The laws that allow space to bend and break are the same laws that allow it to rest. The universe does not need to protect you from its own power. It has already moved past the phase where that power dominated. There is a quiet finality in that, not an ending, but a settling. As the universe expands, as energy spreads, as extremes fade into memory, space becomes less dramatic and more dependable. It becomes a place where moments can linger, where stillness can exist, where awareness can turn inward without interruption. You are held by that dependability now. The energy that never came is a reminder that danger is not the universe's default state. Calm is, continuity is, balance is. And as you lie here, breathing slowly, letting thoughts drift, you are participating in that balance, not resisting it, not questioning it, simply resting within it. Space does not need to prove itself to you. It has already done so across billions of years of quiet endurance. It holds you now as it has always held everything, silently, reliably, without effort. As this quiet journey comes to rest, you are still here, held gently by the same space-time we've been exploring. The energy that once shaped the universe's most dramatic moments has long since softened, leaving behind a cosmos that favors balance over force, calm over collapse. Space continues its silent work, stretching where it must, holding where it can, allowing time to flow without urgency. Nothing needs your attention now. The questions we trace through the fabric of reality do not demand answers tonight. They can remain open, floating softly, like distant stars whose light reaches you long after their storms have passed. What matters is the stillness you feel, supported by laws older than memory and gentler than they sound. If your thoughts drift, let them drift. If sleep arrives, let it come without resistance. You are safe within this vast equilibrium, carried by a universe that has already survived its extremes and learned how to rest. Thank you for sharing this quiet space with me. May the calm of the cosmos linger with you, steady and reassuring as you ease into sleep.